Hi everyone, let's continue. So in the previous lecture, we actually solved the following problem. Do you still remember? The vector field f equals x squared, comma minus xy. Let C be the curve consisting of the parts of the unit circle in the first quadrant. So this is the blue curve, and then together with the line segments from 0, 1 to 1, 0. Okay? Oriented counterclockwise. And we figured out the work done by F along each of the parts of the C is minus 2/3. So on this blue curve, the work done is minus 2/3. And then on the red path, red curve, the work done is 1/2. So the total work done by F along C, we add them together, we get minus 1/6. Okay, and we were calculating using the line integral, right? We found the parameterization for each of the curve, and then we compute the line integral on the curve. Okay, so now let's solve the problem in a different way. Let's use Green's theorem. So you can see this region is connected and simply connected. So we can apply the Green's theorem. Okay, so which means we need to set up and evaluate an appropriate double integral. So what is the Green's theorem? Well, that is the double integral of the curl of f. What's the curl? That is gx minus fy. Well, g, so this is f, this is g, gx is minus y, and then fy is 0. Oh, so the curl is just minus y. So far, so good. And let's see, this is the region, let's call it region R, and we have the curl, and then dA, right? So let's see here. Minus y, let's see, okay, let's do dy dx. Okay, what does dy dx do? Let me use a different color so you can see it more clear. Okay, so dx means we want to cut a small width, dx, and then we draw the rectangle parallel to the y-axis, right? And let's see, the bottom one, okay, what is this line? Well, this line passed through minus 1, 0, 1, and 1, 0. So this is the line y equals, the slope is -1 and the y-intercept is 1. So negative x plus 1. So far, so good. How about the top? Well, the top is on a unit circle, so y is the square root of 1 minus x squared. So y is from minus x plus 1 to square root of 1 minus x squared. And x is from 0 to 1. So far, so good, everybody. So this is the double integral. And let's calculate this double integral. What is the integral of y with respect to y? Well, that's y squared over 2. Evaluate from square root of 1 minus x squared minus x plus 1 dx. So what is that? Well, minus, let's factor out the minus 1/2. Then y squared, oh, square and square root cancel out. We get 1 minus x squared. Is that okay, everybody? Then we subtract, we plug in minus x plus 1 squared, and then dx. What is that? Well, let's multiply out. When we multiply out, it's like x squared minus 2x plus 1, right? And let's get rid of the parentheses. So this is, oh, by the way, we can move the negative back in. Then let's see, we have 1/2. 1 becomes minus 1, but minus x becomes plus x squared. But then now this guy becomes plus, so that we can just copy down the things inside the square, the parentheses. Let's see. Let's reorder it. So we have 2x squared and minus 2x and plus 1 and minus 1 cancel. Oh, we can simplify and divide it by 2, right? So we have x squared minus x dx. So far so good, everybody. Let's integrate. Integral of x squared is x cubed over 3. Integral of x is x squared over 2. Evaluate from 0 to 1. So we plug in 1 first. 1/3 minus 1/2. And then minus we plug in 0. Ooh. So 1/3 is like 2 over 6. Minus 1/2. 1/2 is like 3 over 6. So the answer is minus 1 over 6. Yay! This is the same as our answer before. See? Our answer before is minus 1 over 6. And so it makes sense. It's better to be the same, right? The Green's theorem tells us that they're the same. So far, so good. Okay, so now we have calculated this work done using both methods, the line integral methods and the double integral methods on the curve. Okay. All right, let's continue. Consider the vector field. So 2x squared minus 4y, and then we have 5y plus 1 to the negative 3 plus 3x. Find the circulation or the line integral where C is the triangular loop with vertex 0, 0, 3, 0, 3, 4, oriented counterclockwise. Okay, let's draw it. So 0, 0, 3, 0, 3, 4. Okay, so this is the triangular loop. So far, so good, everybody? Okay, so we have the curve is oriented counterclockwise. Okay, and then this is the region R, right? And if you want to compute the line integral directly, you see there are 3 line segments. You have to split the path into 3 pieces. So on each part, you're gonna find the difference parameterization, and then you want to compute the line integral, and then you need to add up those 3 integrals together, which is quite complicated. So now today, let's use the Green's theorem and calculate the double integral. So what is the curve of this guy? Well, this is f, this is a g, so curve is gx minus fy. Gx. See the beauty? This guy has no x, so it's gone. And this guy, the derivative with respect to x is just 3. Isn't it amazing? And then minus fy. Well, see, 2x squared has no y in it, so it's gone. And derivative with respect to y is minus 4. So the curve is 7. Isn't it nice? The curve is so simple. Then by Green's theorem. Okay, our circulation and line integral equals the double integral of the curl of f on the region R, right? But you know what happened? The curl is a constant. Then we can pull it outside of the double integral. And do you know what is this guy? This is just the area of the region. We don't even need to calculate the double integral in terms of x and y, right? We know this is a triangle. What is the area of the triangle? 1/2 base times height. And 4 and 2 cancel, so we have 2 times 3, 6 times 7, 42. So the answer is 42. Isn't it amazing? Yeah. In general, okay, so in general, if if the curve is not constant. Okay, so yeah, if curve f is not constant, what do you do? Okay, if it's not constant, then you do need to set up the double integral, and you can do dy dx or dx dy. I would like to do dy dx. Then the width is dx. Then you want to draw the rectangle parallel to the y-axis. Well, here the bottom is y equal to 0. The top, well, this is the line. What is this line? What's the slope? Well, the slope is 4 over 3. So this is y equals 4 over 3x, right? So the line is 4 over 3x. So x is from 0 to 3, and then the y is from 0 to 4 over 3x. And then you're gonna integrate this double integral. So far so good, everybody? Okay. So I'm not teaching you only like shortcuts. I also teach you like the general method, how we do it if the curve is not constant. So far so good, everybody? Okay. Alright. Note, the Green's theorem applies directly as long as the curve C is a closed loop and the components of the field F are differentiable. But sometimes Green's theorem can be used in an indirect way. Okay, so when the curve is not a closed loop, let's look at this picture. So C is not a closed loop. So it could happen that the path C, it could be very complicated. This looks like a circle, but it could be something crazy, very, very complicated. Okay, the idea is to close off the curve by adding an edge. See, by adding an edge, now I get a closed curve. Then we can calculate the work done by F along this region. We can use the Green's theorem, okay, because now this guy is, so B is a closed curve. Okay, so F dr and B, we can use Green's theorem. Green's theorem, we can use, let's say this is the region R, we can compute using the curve, the double integral of the curve, okay? And then, look at this piece. This is just a line segment, and usually the parameterization for a line segment is easier, okay, compared to this crazy path, okay? So in this case, then the line integral on C is then the closed line integral on the B subtract the line integral on L, okay? So this is the idea. We first close off the curve by adding an edge, and then we get a closed curve. Then we can use Green's theorem to compute the line integrals, and then we can calculate the line integral, the work done along the line segments that we added. Then we use this guy to subtract the line integral on the line segments to get the line integral on our original curve C. So far so good, everybody? Yeah, so this guy is the original integral along the path C. It could be hard to compute from scratch using a parameterization. And Green's theorem cannot apply directly because C is not a closed curve. Okay, however, after we adding the line segment, the edge, now we get a closed curve. Green's theorem can be used directly to find the integral along B. And now on the line segment L, it is not closed, so Green's theorem cannot be applied directly, but you can calculate the line integral easier because it's just a line segment, right? Usually the parameterization is much easier. And you know what? The parameterization, if you can remember, is just number P0 plus AT and then Q0 plus BT, right? And so when we take the derivative, this is just AB, they're just numbers. So much easier to calculate. So far, so good, everybody? Okay, so this is like a small trick when we have a curve that is not closed. Okay. So here I also do some summarize with you. So I want to summarize this with you. Here is we have some basic flow chart for work or circulation. Okay, the line interval. First questions. Is the vector field conservative? Use the curve test. What is the curve test? Is it Fy equals Gx? If yes, then it is conservative. It is no, if it's in general, if it's no, then it's not conservative, okay? In general, if it's yes, you also need, you remember, you also need the domain is connected and simply connected. Okay? So if it is a conservative vector field, then we can find a potential function. Okay, and then we can use the fundamental theorem of line integral. So the the work done equals the potential function evaluated at B, subtract the potential function evaluated at A. So B is the terminal point and A is the initial point. Okay, so oops. I didn't ask you. So B is the terminal point. A is the initial point. Okay, so work is path independent. We don't really care what the path C is, so don't write the parameterization for it. Okay, and then it really just depends on the endpoint. Or we can use a simple curve L. So usually L is like a line segment just connecting those 2 points B and A. Okay, you can think about L is a line segment connecting A and B. So if the vector field, maybe it is hard to find the potential function, then you can compute the line integral on this curve L, on this line segment. Okay, then it will be equal to the line integral on this path C. So far, so good? Okay, so we have a path C. Okay, and this is A, this is B. And then we can consider the line segment L. We can just evaluate the work done on this line segment L. So far, so good? Yes. So for conservative vector field, path is independent. Okay, what happens if it's not a conservative vector field? If it is not, then first we ask, is the path closed? Well, if it's closed, great. We can use the Green's theorem. So Green's theorem tells us that C is closed, right? Oops. Okay. Then the circulation. Okay. So circulation, we measure how much vector field are going along C. Okay. So that is the double integral of the curve. So we also want to measure like how much vector field are rotating counterclockwise. So far, so good? Okay, if the path C is not closed, okay, then you either try to compute from scratch. So by using the definition of line integral, you want to set up a parameterization for C, okay? So set up parameterization for C, that is R of T, okay? And then you take the derivative of R of T and then you use this definition to compute. Or you can try to close off the curve, just like our previous page. You have the curve C and then we close close of the curve. Now we have a closed curve. So B is like C union L. Then we can use Green's theorem for the closed path, and then we subtract the work along the path that we added. So which we just mentioned in the last page. So far so good. So this is like the complete map when we want to compute line integral. Okay, so this is a basic flow chart for the work done or circulation. So far so good. Yeah, so like first stage, curve test. Is this vector field conservative? Yes or no? If it's no, here, second stage, is the path closed? Yes or no? Okay, and we use different methods. So far so good. Okay, I hope that you can follow this flow map, and then you can do some examples and then understand more. So examples can help us to understand. Okay, next, remember at the beginning of this sessions, we talk about Green's theorem. There are two forms. We have circulation is related to the curve, right? Circulation along the path is like measuring how much vector field are rotating counterclockwise. Now, the other one is the flux form. Okay, so that is the flux. Remember what's the flux? Flux. So if our curve is going this way counterclockwise, flux measures how much vector field are going across it. Wow, across from the left to the right. Well, then this is like measuring how much vector field are going outside of this curve, outside of this loop. Okay. So, yeah, what is the relation between the two, the divergence and flux? So for vector field F, we defined the divergence be Fx plus Gy. If we think of F as representing the velocity field of a fluid in the xy plane, then the divergence measures how fast the fluid is flowing out away from the points. Yeah, imagine C is a small loop and enclose a small area change of A. Then the divergence we measure like flowing out. This is like the flux, right? On that small area. So if the loop is very small, enclosing a very small area, then the flux is approximately equals to the divergence times change of A. So far so good, everybody? Okay, now we have the flux form. C, as before, C is a simple closed smooth curve in the xy plane oriented counterclockwise. And R is a connected and simply connected region in the xy plane that is enclosed by the curve C. Okay, so let's say F is the vector field and both the coordinate functions have continuous first partial derivatives in the region R. Then we have the Green's theorems. The flux, remember flux measure the vector field flowing from the left to the right, okay, across the curve. That will equals the double integral of the divergence. Remember, divergence measure the vector field flowing out. Okay. And so this is how we calculate the flux integral, right? F dy minus G dx. And then for the double integral on the divergence is Fx plus Gy. So far, so good, everybody? Okay, so roughly speaking, the Green's theorem flux form says that the following two quantities are the same. First, the net flux of the field F across the curve C, the outer boundary is the C, i.e. the rate at which the fluid flow out across C. So flow out because the C is oriented counterclockwise, so it's like from left pointing to the right. Okay, and then second quantity is the sum of the source minus the sink. Remember, source is the divergence is going to be positive. Sink the divergence is gonna be negative, right? So it's like we accumulate all those divergences, okay, together. So the sum of the source minus the sinks throughout the interior region that is bounded by the curve C. So far, so good, everybody? Okay, example, use Green's theorem to compute the outward flux of the field f of xy equals xy across the unit circle. So, okay, so this is the unit circle, right? So last time we already calculated this example. Let's see, where do we calculate it? We calculated in the last page of section 14.2. Okay, when we talk about circulation and flux. So yes, and let me kind of remind you, we have the parameterization is cosine t sine t, and then we calculate the flux equals 2 pi. Okay, so this is what we had before. Today, let's use Green's theorem to calculate that, and let's see whether they have the same answer. It should be the same answer, right? Let's see. So here, what is the divergence? Well, divergence, this is f, this is g, right? Divergence is fx plus gy. Well, fx is, well, f is just x. Derivative of x with respect to x is 1. Derivative of y with respect to y is also 1. So divergence is 2. Then, now, the double integral of the divergence. dA. Ooh, you see? Here the divergence is a constant. It's a constant. So we can pull it outside. Now what happened? What is this guy? Oops. This guy is just the area of that region. Well, the area of region R, but R is a unit circle. Pi R squared. But pi r is 1, right? Pi 1 squared. So the answer is 2 pi. Yeah, it's the same. So far, so good, everybody. Okay, let me do a little remark here. So, remark, what if the divergence is not constant? Okay, so if the divergence is not constant, then we actually need to set up the double integral, right? So it really depends on what the divergence looks like. You can choose rectangular coordinates, which is the Cartesian coordinates, or you can choose polar coordinates. So it really depends. Let me do both, okay? I know you want to learn more, so let me do both. Let's if we use the rectangular coordinates, let's say we use the order dy dx. You can also use the order dx dy, but I'm familiar with that. So this means I have a width dx, okay, and then next you're gonna draw a rectangle that is parallel to the y-axis, right? And then what is the upper curve? Well, that is square root of 1 minus x squared. What is the bottom curve? Negative of 1 square root of 1 minus x squared. So negative 1 minus square root of 1 minus x squared, square root of 1 minus x squared, and my x is from minus 1 to 1. Okay, so this is the double integral. If we use polar coordinates, well, then the area differential is r dr d theta. Well, then the r and theta are very easy. Theta is from 0 to 2 pi, r is from 0 to 1. Okay, so it really depends on the divergent function f. If it's not so complicated, maybe it's easier to compute using the polar coordinates. So far, so good, everybody? All right. Let's continue. Okay, more comparison. I know today you have learned a lot, right? We learned 2D curve, 2D divergence, and we talk about circulation and floods, a lot of things together, right? So I really want to make a comparison with you, and then we know we learn a lot, so I want to make this comparison so you can compare different concepts and find the similarities and differences. So then you won't get confused easily, okay? But still, you need more time to think through the math and you need more time to practice, okay? So now we can see a wonderful parallel between circulation properties and flux properties. We need one more piece to complete the picture. It is the stream function, okay? Which plays the same role as like the potential function on the other side. So here we have a rotational field. Do you remember what's a rotational field? That is when the curl is 0. Curl measure like how the vector field is rotating, right, counterclockwise. Okay, if the curl is positive, then it's rotating counterclockwise. If the curl is negative, then it's rotating clockwise. And then on the other side, we have the source-free field. Okay, that is when the divergence is 0. Remember, divergence is measuring the vector field that flowing out from a point or flowing in. So if the divergence is positive, then we have an outward flow. If the divergence is negative, then we have an inward flow. Now, if our vector field is restricted on a connected and simply connected region, then we have the following. Okay, so if F is restricted on a connected and simply connected region, if the curl is 0, then F is conservative. Okay, conserved vector field, it means it's also a gradient field. So we can find a potential function phi such that F is the gradient of this potential function phi. Okay, which means partial phi partial x equals F, partial phi partial y equals G. Okay. And then for the line integral, we have circulation. So circulation F dot dr. Okay, so circulation is 0 on all simple, smooth, oriented, closed curve C. Okay, this is by, we can use the Green's theorem, right? Because this circulation equals the double integral on the curve. Right, that equals the double integral on the curl. But the curl is 0, so that's why this double integral is 0 as well. So far, so good. And furthermore, for conservative vector fields, we have the fundamental theorem on line integrals. Okay, so the line integral equals our potential function plug in the terminal points minus the potential function plug in the initial points. Okay, and this works for all simple, smooth, oriented curve C. So that's why the line integral does not depend on the path. It only depends on the initial points and the terminal points. Okay, on the other hand, so when the divergence is 0, if we restrict F on a simply connected and connected region, then we will have a stream function psi. Okay, so this is called psi, this is called phi. Great letter. Yeah, sometimes I pronounce them wrong. Please forgive me. Okay, so what does the streaming function do? Well, the streaming function, the partial psi with respect to y equals F. Partial psi with respect to x equals minus G. Okay, so this is a stream function. And corresponds to the divergence, we have the flux. Well, the flux measures how much like vector field going across the curve. So this is C. We want to measure how much vector field going across C, right? And the flux is gonna be 0. Why is that? Well, on this is by the Green's theorem. If C is an oriented closed curve, then this flux equals the double integral on the region R of the divergence of F. But because the divergence is 0, so this is 0. Okay? So on a source-free field, the flux is gonna be 0 on all simple smooth oriented curve. And we also have the path independence. So the flux integral is also equals the stream function, plugging the final points minus the stream function, plugging the initial points. See, we have a very beautiful parallel between circulation and flux, divergence and curl. Okay, so please pay more attention on this comparison and try to understand it. And if you have confusion or questions, feel free to ask me. Okay, and I'm very happy to do more examples with you. Examples help us to learn. Each example can teach us something, right? Okay, so Green's theorem. I gave you a summary of the Green's theorem. So assumption, we both assume C is a simple closed smooth curve in the xy plane oriented counterclockwise. And R is the connected and simply connected region in the xy plane that is enclosed by the curve C. And F is a vector field. Both coordinate functions have continuous first partial derivatives. So what is the circulation form? Circulation form, we measure, so we have this C and the region. Okay, so we want to measure how much vector field are flowing along C, right, in the direction of C. So this is the same as we want to measure like how the vector field are rotating counterclockwise, right? So circulation, well, this guy are all circulation, okay? And we usually use this guy to compute. And then the bottom is the double integral on the curve. Okay, so curve measure the vector field rotating counterclockwise. For the flux form, so we have the curve C, and so it's simple closed curve, and also we have a region R, and then let's say the orientation is also counterclockwise, and then flux is measuring the vector field flowing from the left to the right, from the left to the right, from the left to the right. Well, then it just because C is an orientation is counterclockwise, is a closed curve, then this is the same as we want to measure the vector field flowing out. Flowing out, this is a property of divergence. Okay, so that's why the flux integral equals to the double integral of the divergence over the region R. So far, so good? Okay, now that is our Green's theorem. We have two forms, and that relates 4 different concepts. Okay? Alright, so please do your homework. If you have questions, please ask me. Alright, have a nice day.